So what we want to do here is we're going to talk about binary search trees. So right off the bat, I'm going to go into Wikipedia, and this is going to be binary search tree. All right, so they kind of look like this, these kind of dudes, where every node has at most 2 children. All right, so up to this point, we've dealt with linear linked data structures, so linked lists, stacks, queues. Okay, now we're dealing with a non-linear linked data structure. So we're still linking things together, still have our node type things, at least for right now. But at the end of the day, what are we doing? We have this is a non-linear fashion. Okay? So at most in a binary tree, binary meaning 2, right? We get a maximum of 2 children. So this node has 2 children. This node has 2 children. This node has 0 children. This node has 2 children. This node has 0. This node has 0. Typically, nodes that have 0 children are called leaf nodes. All right, so let's give some definition to that. So, binary trees. Nodes may have a max of 2 children. Nodes with 0 children are called leaf nodes. Make sense? Just kind of normal saying for this. All right. And so let's start off by talking about the organization of these trees. Okay? As we're looking at this tree here, so here's an example of a binary tree. Binary trees have values stored in order. Okay? So notice that everything to the left of this 8 is less than it. 3 is smaller than 8. 6 is smaller than 8. 1 is smaller than 8. 4 is smaller than 8. 7 is smaller than 8. Everything to the right of this is greater than or equal to the 8. 10 is greater than 8. 14 is greater. 13 is greater. Same thing's true at any individual node. Take 3. Everything to its left is less than. Everything to its right is greater than or equal to. Okay, 6 is greater than or equal to 3. 4 is greater than or equal to 3. 7 is greater than or equal to 3. 1 is less than 3. Now the reality is you can flip where the equal is. You can say everything to the left is less than or equal to. Everything to the right is greater than, if you want. But the punchline is that binary trees are guaranteed to store information in an ordered way. Now, how we actually interpret that information to pull order back out is what changes things, okay? So, looking at this initially, when we look at this tree, let's kind of start off a simple tree. Oh, that's not what I want. I want this guy. So let's say I have a 3, the top node of this tree. All right, and now I want to add a 5 to this tree. When I try to add this 5, I'm going to drop it into the top of the tree. And we're going to say, okay, well, is this position available? No, it's not. Is a 5 less than 3, or is it greater than or equal to 3? Greater than or equal to 3. So we're going to try to add it to the right child of 3. It just so happens that 3 does not have a right child now, so we'll go ahead and drop the 5 there. We have an available spot. All right? Every node in a tree has at most 2 children. Okay, so there is kind of an empty bucket sitting right here and another empty bucket sitting right here. And since we've decided that 5 needs to go to the right of the 3, since there's an empty bucket there, we'll just drop it in. Now I'm going to do a 4. Try to drop a 4 in here. Should a 4 come before a 3 or after a 3? After. Should a 4 come before a 5 or after a 5? Before. So we'll drop it here to the left. It's available. Make sense? All right. So kind of understand the makeup of binary trees? All right. So we want to think about these nodes here for a second. So what is a node of a tree? A node of a tree is a payload, 5, and then a left node and a right node. That make sense? So let's build this out a little bit more. Let's give ourselves a 2 here. We'll spread this out. And then we'll give ourselves a 1.
Each node is parent?
Doesn't. Node does not know who the parent is, at least not in the default implementation. All right, so let me ask you this. That whole thing is a binary tree, correct? Okay. Why? Why would you say that's a binary tree? What's the definition of a binary tree based on what I've just explained?
Each node has 2 children, at maximum 2 children. And the left node payload is less than the.
Okay, so there's 2 levels, right? A binary tree is a tree where any subtree, and I just give you a hint there, any subtree has at most 2 children, and the things to the left are always less than, or you can say less than or equal to, and the things to the right are always greater than, or greater than or equal to, depending on which side you chose to put the equal sign on. That's the definition of a binary tree. So this whole thing is a binary tree, isn't it? Is that a binary tree? Does this guy have at most, does every node in here have at most 2 children? Is everything to the left smaller than everything to the right? Yep, that's a binary tree. Is this a binary tree?
Yeah.
Does he have at most 2 children?
No. Yes.
At most, he has 0 children.
Yeah.
So at most, he has 2 children, right? So this does not break the rules of a binary tree. Is everything to the left of this guy smaller than him? Yeah, there's nothing over there. Is everything to the right of this guy smaller than him? Yeah, there's nothing over there. So is this a binary tree? Yeah? Is that a binary tree? Is that a binary tree?
Yeah.
Is this guy a binary tree?
Yeah.
Yep. So is it fair to say that a binary tree is a tree of binary trees? Make sense? Where a binary tree has a value and a left and right child. Make sense? All right. So let's go into here. Let's create a new project. Driver in here. All right. So we're going to create a class called binary tree. So new class, binary tree. And we decided that binary trees will have a private, we're going to start this guy, we're going to make a, just like we did with linked list, we're going to make this guy a tree of integers. Okay? So private int payload, private binary tree, left tree, private binary tree, right tree. Who? This guy? Oh, I mean, you could make it R capitalized, but I have this naming conventions correct the way I have it. I mean, you could make it capitalized if you want, but usually variable names start with a lowercase letter, more of a naming convention thing. Public binary tree, so the constructor for this guy is going to take in a payload And we're going to say this dot payload is equal to payload. This dot left tree is equal to null. This dot right tree is equal to null. All right, so that is our base binary tree. Okay, so a binary tree is a tree of trees. Now at some point, we have to keep track of the top of the tree. Does that make sense? So we don't know, we can't get, just like in our linked list, we can't get to other nodes in the list unless we know where the top, the front of the list is, the head. With a tree, we need to keep track of the root node of this guy. All right, so a binary tree has a root node. Let's go back here. Let's think about writing this though. What we just created is a binary tree. This 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 is a binary tree. But this entire thing here needs to be stored inside some kind of object, right? Okay. So we need to come up with a name for that object. So we've decided that our binary tree is a tree of trees. We need to have an object that's going to store our tree of trees. So we're going to create another object here. We're going to call this guy a B tree. And our B tree is going to have a private binary tree called root. Public B tree. We'll initially set this dot root equal to null. So now we need to be able to add things to our tree. Okay? So whenever we add something to our tree, we're always going to be adding a brand new tree. Okay? So I'm going to go ahead and say binary tree, new tree, is equal to a new binary tree built around our value. Pretty similar to what we did before, right? Mm-hmm. Now we're going to try to add this tree to our current B tree. Mm-hmm. If this dot root is equal to null, then this dot root is equal to new tree. Else, we're going to try to add our tree to our root. So now we need to know how to add a binary tree to a binary tree. So we'll go into binary tree. Of a public add. Okay, and this guy is going to take in a binary tree as a parameter. Let's call it BT. All right. And we're going to try to add this binary tree to this tree. Now, we need to determine, we wouldn't be adding it to this tree if this tree didn't already have a value. But now we need to determine, should BT go to the left or should it go to the right of this tree? Okay. So we need to do this, but we need to have access to BT's payload. Okay. Now, does that mean I have to give myself a getter for BT's payload? Or can I access BT's payload right here? Can I say BT.payload? Is that legal? It is legal. Tell me why. What kind of animal is this guy? He's a binary tree. What class am I currently in? Binary tree. What kind of variable is payload? It's a private int. Private ints are only accessible inside where? The class in which they were defined. The class this guy was defined in is a class called binary tree. Are we inside a binary tree? We are. Okay, so this is how private variables work. We actually don't need a getter for this guy. All right, so now what I can do is I can ask, okay, well, which side should this fall on? So do we want to have everything to the left be less than, and everything to the right greater than or equal to, or do we want to have everything to the left be less than or equal to, and everything to the right be greater than? Less than or equal to the left? All right, fine. So if this dot payload, well here, let's since we'll just stick with.
Should we determine if it already has two leaves already?
Well, it doesn't matter at this point. We need to know where we can try to add it. We know once we know which side it should go in, then we can find out, is there an opening? If not, add it. All right, so you'll see that here in a second. So we'll go ahead and grab the payload. So we're going to say, is the new guy's payload less than or equal to this guy's payload? If it is, we want to add it to the left. Okay, but what if he doesn't have anything on the left? If this dot left tree is equal to null, then we can say this dot left tree is equal to BT. I can just go ahead and set it, right? Else, this dot left tree dot add BT. Now if I'm in this else here, this else says that it must need to go to the right. So if this dot right tree is equal to null, this dot right tree is equal to BT. Else, this dot right tree dot add BT. All right, and this guy needs to be a void. So public void add binary tree BT if BT should come to the left. Is there an opening to the left? If yes, just put him there. If no, ask the left node to add BT. So it trickles down through the tree. Does that make sense? All right. Else, it must need to go to the right. If there's already an open spot on the right, just put him there. Otherwise, add him to the right. Make sense? All right. So that is our binary tree. Let's go into driver here. So I can say B tree BT is equal to new B tree. And then I can say BT dot add an 8. BT dot add 4. BT dot add 7. Just start off with the simple thing here like this. So we'll add an 8, that'll be the root. 4 will go to his left, 3 will go to his left. Let's add a BT dot add 9. Okay. So we just built a tree. But now let me ask you something. If we look at B tree here, what's the difference between, well, let's see, do I want to ask that? I'm going to ask that next time. It'll make more sense when I ask it next time. Because right now we're storing primitive type integers. Punchline here is we don't actually need B tree. We can actually do all this with just binary tree. But since our payload is an int, we can't give it a null value. So we can't ask, does this guy have a value? If he doesn't, make this guy the value you're trying to add. Otherwise, add it to the appropriate child node. Okay? So for right now, we'll leave it as B tree. It's not going to hurt anything. All right, so we'd like to now be able to display our tree. Now the problem is this looks all pretty when we look at a tree displayed like this. That's a little bit difficult to do in text. All right, so what we really want to do is we want to deal with our trees at various levels. All right, so we just built the tree that's effectively an 8 with a 4 to its left, with a 3 to its left, and then a 9 to 8's right. That's what we effectively just built. Okay? So that guy will look like this. It's an 8, it's a 4, that's a 3, that's a 9. That's the tree we built. We're going to say that this is level 0. We're going to say that this is level 1. We're going to say this is level 2. Make sense? All right. Now, whenever something, and then we're going to say that this guy is the left node of this guy. Make sense? So this guy's address, if you will, is level 1, position 0. This guy's address is level 1, position 1. This guy's address is 2, 0. And this guy is 0, 0 at the top for our root node. Make sense? So the very top of the tree will always be 0, 0, 100% of the time. His left node is always going to be 1, 0. His right node will be 1, 1. Because this entire level here is level 1. This is left node is 0, right node is 1. You could also say this. You could say left, right, if you prefer to look at it like that, right? Okay. Now, what if I had multiple nodes here? So let's go. So we have 5. And then greater than that, so let's give ourselves a 9. And then give ourselves a 10. What should the address of these be? So this was 2, 0.
I think it should say 2, 1, 0, 2, 1, 1. 2, 0, 0, 2, 0, 1.
Okay, well, first of all, do we like the left rights better? So this is 2.
0, 0.
So we're already in the left tree. So this is left, left. This guy is 2, left, right. Okay. This guy is 2, right, left. And this guy is 2, right, right. That make sense? So when we display something, we need to know which direction we went, all right, and then where we currently are. And we need to build up this address, all right? So every level we went down, we incremented this value by 1. This was 0, then 1, then 2. When we went to the left, we added an L. We went to the left again, we added another L. Okay, so we have a level, and then we have a position in that level. That make sense? And this is the most complex it can get, right? I can go down to level 3. And these guys, so I'll just keep adding on letters. Okay? So when I display, I need 2 things. I need a binary tree needs to know about his level, and he needs to know about his direction. Okay? So let's go back up here, go into B tree. We'll go ahead and write our display method. Public void display. All right, so we'll ask the question if this dot root is equal to null. We'll just say system.out.println empty tree. Else, if it's not equal to null, we want to go ahead and get this first guy's payload, right? We want to get this first guy's payload and ask him to display himself. So that means that we're going to go ahead and say this dot root dot display. So we're going to teach binary trees how to display themselves. So let's go into our binary tree. Public void display. All right. So this guy needs to know about the level, correct? He needs to know about the level, and he also needs to know about his position, direction, whatever, right? All right. So if you look at what we were doing here, based on what we said, otherwise, wouldn't this guy's address be that?
Yeah.
He's neither left or right. It's just 0. So we'll take in an int level, and we'll take in a string position. Okay? And then what will we print out? We're going to print out our payload followed by an address. So we'll say system.out.println. We'll do printlns, that way they keep kicking down a line. And we're going to say this dot payload concatenated with, well, yeah, put a space in there. So concatenated with level, concatenated with maybe a colon. Do we do colons or commas? We did commas. That's fine. Do we put them right next to each other? So dumb. And then we'll do position. Like that. So this will print out this guy's position, right? Then we'll say if this dot left tree is not equal to null, then we're going to say this dot left tree dot display level +1, and position will be position concatenated with a comma L. That make sense? Empty string concatenated with an L. L concatenated with a comma L. All right. Well, actually, if it was already an empty string, then we just want to set it to L. If it was not the empty string, then we want to set it to, we want to add a comma followed by L. So I'll show you a nice little shortcut for that. So we're going to take position and we're going to concatenate onto position. Let's see if I can show you kind of a cool little codey thing here. So position dot length question mark, let's see, equal to 0. Position.length is equal to 0. Colon. Boil down to L. This is a question mark. Yeah, there we go. So this is an inline if statement. So I'm asking the question, if the length of position is 0, boil down to L. Otherwise, boil down to comma L. Saves a line. I wouldn't necessarily recommend this, but wanted you to be able to see the syntax. So this guy right here is called an inline if statement. One of these two things will be what this entire line boils down to here. So we'll either concatenate on an L or we'll concatenate on a comma L. Make sense? All right, so that's if the left tree is not equal to null. Steal this here. Else, if the right tree is not equal to null, then we'll tell our right tree to display the level +1 and either an R or a comma R. Make sense? All right, so now our binary trees know how to display themselves. So now go up to B tree. To get the ball rolling here, we're going to pass it a 0 and the empty string. See, the top level of a B tree is level 0. And it has no left or right. That's why we passed in the empty string. So we would expect the output of this program, the display for this, to be this. 0, then 1 comma L, then 2 comma L comma L, then 2 comma L comma R, then 1 comma R, then 2 comma R comma L, then 2 comma R comma R. So that would be the output that our things should get, because we always check the left child first before the right child. So we display this guy, then if he has a left node, tell his left node to display himself. He displays himself right here. If he has a left node, tell his left node to display himself. He displays himself. He doesn't have a left, he doesn't have a right, bounce up. Now this guy has a right, yes. Tell him to display himself. Doesn't have a left, doesn't have a right, bounce back up, bounce back up. This guy's right. That's the 1R. Does he have a left? Yes. Tell him to display himself. No left, no right, bounce back up. Does this guy have a right? Yes. Display himself. No left, no right, bounce back up, we're done. So this should be the output of our program if we displayed correctly. So let's go into our driver and we'll say bt.display. Doesn't look like what we should have had, but does it? I just see one little value here. Let's go back in here. What did display say to do? It says call the root node, tell it to display itself. Here's the root node. Root node displays itself. And then we say if the left tree exists, do this. Else if, wait a minute. This is not an else if, it's just an if. We want to check both the left and the right tree. It's not one or the other. If you have a left tree, tell him to display himself. If you have a right tree, tell him to display himself. Okay? Still stuck there. So we got to look at our add method, because the add method seems like we maybe be zigged when we should have zagged. All right, so we're definitely getting this guy displayed correctly initially. But we're never getting in here. If left tree is not equal to null. So let's go ahead and let's look at add. Add, we're saying if btree.payload is less than or equal to this dot payload, if this dot left tree is equal to null, this dot left tree is equal to bt. Else this dot left tree add bt. Okay, that should. All right, so let's trace this then. let me put breakpoint here, run it through the debugger. All right. So here's our root, left tree, right tree. So he doesn't have a left or a right tree, even though we've already called display. So that means something's broken in our add. So let's go back here, toggle this off. Let's go into add here, toggle this on, stop it, run it. Let's do it right here. All right, so there's our BT add. So let's step over there. So BT add should go into our B tree. We try to add. Yeah, we try to add. We build our binary tree here. If root is equal to null. Yeah, we gotta finish writing this. So this dot root dot add new tree. Okay, should be in a little bit better shape now. I was testing you and you all failed. That guy off. Let's just run this. All right, so here's the left, one right. All right, this guy still didn't get completely built. We should have all this.
So you don't have that many. Elements. You only add 4.
Oh, thank you. So I need to do a. So I already. Well, okay. Let's just get it back to this. So I need to do an 8. Then I can add a 4. Then I can add a 3. Then I can add a 5. Then 9, 9, 10. So right now I've done 8, 3, 4, 9. Oh, 8, 4, 3, 9.
5, 9, 10.
So this is the 5. Then another 9. Then a 10. So 8, 4, 3, 5, 9, 9, 10. 0. Oh, this is going to be, let's do, so this is 8, 0, 4, 1L, 3, 2LL. Did we get that? 3, 2LL. Then 5, 2 LR. 5, 2 LR. Then 9, 1R. So 9, 9, 1R. Then 9, 2RL. And then 10, 2RR. Okay, so seems like it's traversing our tree correctly?
Yeah.
Or at least displaying our tree in a reasonable way. Okay, fair enough. Now, go back here and let's look at tree traversal. There are various ways that we can go through a tree. Now, the stuff is being stored in a tree in a searchable way. It's in a certain order, right? Okay, so for instance, we can sort a tree. We can search a tree. back in here, go to the Java view. I can build into my tree a public Boolean search int value. And I can say if this dot root is equal to null, return false. Definitely not in there. Else this dot root dot search for value, and we'll return this. So now we're going to teach each binary tree how to search itself for a value. Public Boolean search int value if this dot payload is equal to the value, return true. Else, if value is less than or equal to payload, if this dot left tree is equal to null, return false. Else, return this dot left tree dot search value. Else, if this dot right tree is equal to null, return false. Else, return this dot right tree dot search value. Okay? So when a binary tree searches for a value, the very first thing it does is it says, is the value you're looking for me? That's what this says, right? If my payload is the value you're looking for, return true. Found. You got it. Else, if the value you're looking for should be to my left, that's what this guy says, and I have no left tree, sorry, I've run out of places to check. Return false, not found. Otherwise, let me go ahead and ask my left tree to search for you. We'll pass the buck, and we'll return whatever my left tree has to say. Otherwise, this else says, if the value should come to the right. If I don't have a right tree, sorry, you're out of luck. I already searched all the places. Return false. Otherwise, I'll ask my right tree to do the work for you, and I'll return whatever his answer was. Make sense? All right, so now we implemented search like that. All right, so let's go out to driver. And let's do a system.out.println bt.search for an 8. We should get a true, right?
How about if you search for the 9? We have 2 9s here.
Oh, it'll find it. We don't know which one it found, but it'll find one of them.
Probably will find the first one.
So we should get a true, true, false? True, true, false. All right, so now it's seemingly searching. Is searching a binary tree efficient?
Depends.
Well, so it depends. What does it mean for something to be efficient?
If you go through everything.
Is searching a binary tree more or less efficient than searching a linked list from beginning to end?
That is more efficient.
Which is more efficient? So I have a linked list. In this linked list, I have 100 numbers. Okay, and I'm searching, and they're not in any order, just 100 numbers. Okay, and I'm going to search this list of 100 numbers for that value. What's the minimum number of things I'll have to check?
Wow.
1. What's the maximum number of things I'll have to check? 100. So minimum is the very first, I'll find it my very first check. Maximum is I'll check all of the guys and either find them on the last one or not find them at all, right? So giant difference between finding it early or finding it late or not finding it at all. Okay? Binary tree. So I have a binary tree with 100 numbers in it. What's the minimum number of things I'll search to find? 1. What's the maximum number?
50.
Log
Less than 50.
log n.
It's log of n. I keep cutting my information in half, and half, and half, and half, and half, only checking in the spots where the data might be. Okay? So if I start searching through this tree, and I'm looking for the 7, let's say, I'll come here and I'll say, okay, is this the 7? No. Should the 7 be to the left or to the right?
Yeah.
Should be to the left. So from that point forward, the right side of this tree is dead to me. Never going to look at it again for this search. So now I'm only looking over here. So I check the left node. Is this the guy I'm looking for? No. I've looked in 2 places so far. Okay. Is the value I'm looking for, should he be to his left or to his right? The right, over here, right? I'm looking for a 7. So we're going to ignore this guy as if he never existed. Come here. So I've already cut out 3, 4 nodes that I will never check.
Yeah.
Okay? So I go to the right. Is this the guy I'm looking for? Nope. Should he be to the left or to the right? It should be to the right. So now I've cut out another node that I'll never check. Is this the guy I'm looking for? Yes. Okay? Now let's say I was looking for a 7. Or let's say not a 7. Let's say I was looking for a 7.1. Just to make this work. Okay? This isn't the guy I'm looking for. Should he be to the left or the right? He should be to the right, but I have nothing else. I'm done. Okay? I skipped large chunks of this tree. Okay? And I didn't just cut it in half. I cut it in half, then cut that in half, then cut that in half, then cut that in half, right? Okay. Now, technically, a binary search tree we can say is order log n in terms of big O notation, which is the performance of it. But we actually we maximize the performance of it in a situation where we keep our tree what's called balanced. Okay, and that's something we're going to talk about more next week. But, this tree is a balanced tree. All right, that is, one side is roughly the same depth as the other side. That's a balanced tree. Now, an unbalanced tree would be a tree that's very left or very right heavy. Okay. Yeah, to the point where you basically have a linked list, right? So that would be a tree that you're not gaining a whole lot of performance from because the tree is not maintained, even though it's in order, it's not maintained in an efficiently searchable format. Does that make sense? So we would have to keep our trees balanced, and that's what we're going to talk about next week with something called Abl trees. Now, having said that, if I take the same numbers, okay, same set of numbers, like this, and I add them to this tree in a different order, will it produce the same tree or a different tree? So if I add these exact same numbers, 8, 4, 3, 5, 9, 9, 10, but I mix it up, I no longer am adding it in this exact order, I jumble these, right? Will it produce a different tree?
Probably different.
Very likely a different tree, right?
Yes.
It's possible the moons align and it won't, but punchline is that the order in which I add elements to a tree don't necessarily dictate what that tree looks like. It's what has been previously put into that tree that will dictate where this value will finally live. That make sense? Okay, so the order in which we add stuff to a tree can change the way the tree ends up being built. If I add the 4 first, that's my root node. If I add the 4 first, and then I add the 8 after it, the 8's going to be to the right of the 4, as opposed to the 4 being to the left of the 8. Make sense? So little tiny changes make a big difference. Now, we don't necessarily have control over the kinds of values we're going to be putting into a tree. All right, but we saw already that this tree data structure is pretty flexible. I'm going to go in here just so you have access to a random number generator. I'm going to go ahead and give myself, let's see, random r is equal to new random. Java.util. And let's go ahead and say for int I is equal to 0, I is less than 1,000, I plus plus. And we'll go ahead and say bt.add r.nextInt. Let's give it 250. So that'll give me a number between 0 and 249. And we'll add 1,000 of those numbers to our tree. Okay. Well, I guess we can see if we found those specific numbers. All 3 of them were in our tree. Okay. 8, 9, 14 all made the random roll. Okay. But see here, look how complex that tree got pretty quick, right? Isn't that pretty cool? Okay, now what's interesting about this is, and what I kind of want you to start thinking about is, remember first class, we were talking about what's a data structure. And I mentioned we're going to be talking about our traditional data structures in here. Linked lists and stacks and queues and trees and stuff like that. But really, anything that's an object is a data structure. So we want to think about our data structures as kind of like Legos that we're using to build more complex things. All right? So now in this particular case, we would say that a binary tree, the implementation of this, fairly simple. The complexity is not in the implementation. The complexity is in the structure, right? Okay, so let's take a skyscraper as an example. Okay, so they built the Empire State Building, a famous skyscraper, right, in New York. So if you go back and watch one of these videos of them building the Empire State Building, what are you going to see? You're going to see them doing the exact same thing over and over again. Steel girders going up, steel girders going across, steel girders going up, steel girders going across, just steel, 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 all the way up to the top, right? Okay, and then they put some siding on it and said, okay, this is safe. All right. So what we did here is the exact same thing. Every level of our tree is built identically, but when we look at this here, this is certainly structurally representing our data in a complex way. If we look at any individual part of the Empire State Building, it's simple, right? A couple of steel girders put together. But we look at the entire thing, it's amazing how it doesn't fall over. It's this hugely complex thing. If we took all the sides off of it, wouldn't it look like a puzzle? It would look kind of like this looks, right? All these things that each individual spot isn't that difficult. But when you put it all together, it's kind of difficult, right? Okay, so now let's kind of prove a point here. Instead of returning a Boolean, what I want to return is the number of places I checked for a value. Okay? So we're going to have a version of search. And instead of this guy returning a Boolean, yes, I found it, or no, I didn't, I'm going to have it return an int. Okay? In the event that we have no list, we're not even going to check anything. We found your answer in 0 checks. Okay? I guess if we want, we can say that's technically a check. Okay? It took us 1 check to see that you just asked the empty tree if there was something in there. Otherwise, we're going to return 1 plus this dot root search value. So let's go into this guy. We're going to change search in this guy to no longer return a Boolean. Now he returns an int. Okay? If we find this here, we're going to go ahead and check it. And at this level, it's not 1 plus, it's 0 plus. Right? So actually not even 0 plus, just this. Because our first check technically will be right here. So now we have int search. If we found it, return a 1. Else, if we didn't find it, still return a 1. I still checked. Okay? I looked here, I couldn't find it. I checked once. Otherwise, return 1 plus this. 1. 1 plus this. Make sense? All right. So now our search is going to give us no longer a true or false, but how many places we looked to find the value. Let's go back to driver here. 755. Not very many places considering we had 1,000 elements. Make sense? What if I take that up to 10,000 elements? And that's not even a balanced tree. We're just hoping this tree is somewhat balanced, right? This is literally a roll of the dice to determine whether or not we get the values in there. You know, in the any sort of structural order. 100,000? Yeah. But now what's interesting here is even though we have 100,000 values, we only went down 249 levels. Our tree got very, very, very wide, but it didn't get that tall, relatively speaking, right? 9, 10, 12 was the number of things we checked to find those values. So as our tree gets bigger and bigger and bigger, the search time doesn't scale equally. Does that make sense?
By the way, there is one thing. Is it because we are using random? For example, if we are adding 1 to 10,000 to the tree, probably it will be
Oh, okay. If I'm, instead of using random numbers, if I did this, add I.
Yeah.
Okay? So let's not display it this time, right? That way,
we should change the
Thank you.
time.
100 or 1,000.
Yeah, it will be exactly 8, 9, 12.
oh, that's fine. Yep. So here we can.
Number 81 or
So you want to search for an 81,
999.
Yeah.
and 14,400.
That'd be like a string.
It takes time.
Make it less than 10,000.
Oh, actually, hold on a second. I run out of stack space. Yeah.
Yes.
Make it only 100 or 1,000 maximum.
Just 1,000.
1,000, yeah, that's better.
All right, so that's fine.
And for the 14, whatever,
Yeah.
1,000.
So we didn't even find these two. Well, actually, we did. We found the 999.
That's why you search 1,000, but you couldn't find it.
It's because if we're adding things randomly, it's more likely it will
More
be
likely it's going to
unbalanced.
spread out. Yep.
It will be unbalanced.
Well, it's less likely that it'll become a linked list. Yeah, we're not saying anything about how balanced it is. We still might have one side that's 50 or 60 depth bigger than the other side, right?
But no way like linked list.
Correct. All right, so now let's talk about traversal. All right, so we have multiple ways of traversing a tree. We have in order, post order, and what are they going to call it? The okay, yeah. So we have in order, we have pre-order, and we have post-order traversal. This is how we visit a tree. All right, so let's look at in order first. So in order tree traversal, this deals with how we visit things. Do we do depth first or breadth first? And we'll talk about that as well. So in order, let's look at an example of in order here. In order visits this A, B, C, D, E, F, G, H, I. A, B, C, D, E, F, G, H, I. So this is depth first, right? So we go all the way down here to A, then bounce up, visit his parent. So we do depth, then this guy, then try the right child. But before we visit this guy, we visit here, then bounce up, then here. So it's always go as far left as we can, visit, bounce up, visit, go down, visit, bounce up, visit, down, no more down, visit, up, visit, down, can't go down here, visit, go down here, visit, bounce up, visit, nothing here, we're done. Make sense? So let's go ahead and write a display in order. All right, so we're already convinced that we have a display method here that gives us that address. That kind of is proving the structure of our tree. Okay, realistically, when we are looking through the tree and looking at the values, we're not so interested in the structure as long as we can trust the structure. Okay, so the point I want to drive home here with the binary trees is that the structure is what's important. Okay, how we're representing the data inside of this structure, that's the important part. Okay, so we're going to say public void display in order. Okay, so this is going to do an in order traversal of our tree. All right, so we'll say if this dot root is equal to null, system.out.println, empty tree again, else we need to visit the node in order. Okay, so we're going to say this dot root dot visit in order. So I have to write that function. All right, so we'll go into our binary tree here. Public void visit in order. And what did we decide visit in order does? It's a depth first. So we try to go to the left node first. Then we visit ourselves. Then we try to go to the right node. All right. So if this dot left tree is not equal to null, then this dot left tree dot visit in order. Make sense? Then system.out.print this dot payload, and then we'll just put a little space after that. Okay. Then if this dot right tree is not equal to null, this dot right tree dot visit in order. So visit in order says try the left tree, then do myself, then try the right tree. If I were to print out this tree, so right now we have our driver, and this guy, right now this guy does some bad stuff, right? Let's get back to random stuff, okay? So this guy does, let's just go back to 1,000 numbers between 0 and 249. Get rid of the searches. And then we say bt dot, what I call it, display in order. What will my output look like here?
Small numbers and then
That's in order. See how that worked? So in order, because of the structure of our binary tree, in order guaranteed that we visited the values in numerical order. Make sense? Okay. Now let's look at pre-order. What does pre-order say to do? It says visit the self first, then visit the left, then visit the right. Make sense? Visit myself, visit myself, go to the left, visit myself, nothing to the left, nothing to the right, go to the right, D, visit left, C, visit right, E, bounce up, here's the G, visit myself, nothing to the left, go to the right, here's the I, visit myself, here's the left, here's the H, so on and so forth. So pre-order says visit myself first, then go to the left and right child. Let's go into B tree. Just steal this function here. Display pre-order. Display or visit pre-order here. We'll steal this. Say this is visit pre-order, and pre-order just says visit yourself first. Visit yourself pre-visiting your children. Then try left, then try right. Make sense? So, come out here to my driver, and I say display pre-order. Let's go back and look at this. Pre-order gave me F, B, A, D, C, E, G, I, H. Why would I use pre-order? So look at this like it's the alphabet. So that's our alphabet. That's the way I'm visiting the alphabet. What's the advantage of that?
do random division. Instead of visiting.
Look at the output.
Let's start from root.
There's the root.
The root was 250 something, so most would be on the left.
What's funny is those guys actually ended up looking more in order than they probably should have.
Yeah, because the rule was 250, 2 something, so everything was on the left.
Yeah, it was just bad luck.
Can you try again? See the first number? It was 250. 183. I mean,
usually use random
58.
500.
Yeah, that makes more sense.
But it still seems like still the it's in order.
We're visiting correctly, aren't we?
Are you writing the correct?
Display. I don't think so. Visit pre-order. Oh, it's visiting these guys in order.
That's a reason.
There we go.
It makes sense.
All right, so coming back here, looking at the structure of how it visited this. For pre-order, it always checked this guy first, then went down. When would we check? When would we do things in a pre-order fashion? When does pre-order make sense? Searching. Yeah. We don't want to skip past the value we might be looking for. So visiting in pre-order gives us the opportunity to find the value now rather than stumbling upon it later. Make sense? So pre-order seems ridiculous from a structure perspective, but from a searching perspective, it's exactly what we want. We want to find the value as early as possible. So we want to make each node visit, each tree visit, count. Okay? So that's pre-order. What about post-order? Post-order says A, C, E, D, B, H, I, G, F. So it's dealing with the depths of this first. Okay? So let's go back here. B tree. Display post order. Visit post order. Binary tree. Visit post order. Post. Post. Oh, yes we do. Post order says this guy goes here at the end. Visit left and right first, then visit the node. That's post order. Okay. Now, when would you use post order? We're using the exact same structure, but we're looking at different ways we can traverse that structure. When might post order come in handy?
When you want to set bottom-up approach.
Bottom up, when things in the leaf nodes are the important things. So depending on the types of data that we're storing, if the data that we're representing in our binary tree happens to have important stuff that syncs, that's down around the leaves, doing a post order is going to get us to that information, search that information more quickly. All right, so pre-order gives us the best approach for generic searching, where we don't know the nature of our data, right? We just know our data is in order, whatever that means, okay? Post order gives us ideal searching when depth first, when the data we might be interested in happens to be bottom heavy. Okay? In order, what's the value, what's the benefit of in order?
You want some least numeric
Yeah.
strength.
Extracting the values out of our tree in the order it was stored. Okay, so in order is not a search thing, right? In order is a data representation thing. Right? There's really no rhyme or reason to searching something in order versus something else. It's, hey, look, this tree structurally holds your stuff and there's order to it. If you'd like to see what that order looks like, visit it in order and you're going to get the values in order. Okay? Now here's this thing called level order. Okay, sometimes this is called a breadth first search as opposed to a depth first search. So this was kind of a depth first search, right? We went all the way down to the depths and bounced back up. This guy's a breadth first search where we kind of search it one row at a time, one level at a time. How would we implement this? So we visited the F first, and then we visited the B, and then the G. But how? Yeah, but that's not how my tree is structured. So think about how easy the previous three were to implement. Okay, now if we want to implement this guy in breadth first order, I'm going to visit F. And then the very next thing I'm going to do, I have to choose, am I going to visit his left or I'm going to visit his right? Well, if I'm going to visit his left, which is what it says to do, that's B, the very next thing I need to do is visit his right. That's before I visit that guy's left. So how do we implement breadth first? Doesn't this seem problematic?
There's no easy way.
Same exact tree that we had up here. Except when we visit the tree, we'll start at the top. That's the easy part, right? We can visit F first all day long. Okay. So we get F. That's a pre-order search so far, right? Pre-order visitation, get the F. But then we need to visit his left and his right before we do anything else. What about using one of our other data structures? Maybe a stack? Could I, if I take this F, I push it onto a stack. Then I visit the B. I push that onto the stack. And then I visit the A. So this is really a pre-order. So here, then here, then here, then here, then here. So this is all pre-order traversal, right? So if I visit these guys in pre-order, which is this guy right here, I get F, B, A, D, C, E, G, I, H. Could I put these guys on a stack in an interesting way to ultimately give me my values in the order I'm looking for? At the end of it, I need F to be on top of the stack. That should be the very first guy I pop. What do you think? Let's play with this a little bit. Give myself this guy. Oh. So there's my 8. All right. So we start going through our tree, and let's start building a stack. Okay, then we'll try to decide how I might need this stack to be represented differently. So I just hit the F, then I hit the B, then I hit the A. Now when I bounce back up from the A, the next thing I'm going to get is the D. So we'll just put them in the stack in the right order for right now. Then I'm going to get the C. Then I'm going to get the E. Then I'm going to get the G. Then I. Then H. All right, now if I just pop off the stack like this, I'm not going to get the order I'm interested in, am I? So maybe I need to apply some rules to how I push things onto the stack. Am I probably going to push F on right off the bat? Yep. So now I get to the B. I'm going to visit B. So when I visit B, I'm going to go ahead and push it on the stack. Oh, actually, let's bounce off here for a second. Copy it. Then I'm going to visit the A. And push that onto the stack. Okay. Now I'm at the end, right? F, B, A. I have nowhere else to go. So when I bounce up, I could pop this guy off the stack and push him onto a different stack. Then I'm going to hit the D. Then I'm going to hit the C. Then I'm going to bounce back up, pop this guy off, put him on a different stack. Then I'm going to hit the E. Then I'm going to bounce back up, pop him off the stack. Then I'm going to bounce back up, pop him off the stack. Then I'm going to bounce back up, pop him off the stack. Then I'm going to bounce back up, pop him off the stack. Let's deal with the other side here. I'm going to put the F back on here for right now. We're going to visit the G, push him onto the stack. Then we're going to visit the I, push him onto the stack. Then we're going to visit the H, push him onto the stack. And the H is going to come off, pop. I is going to come off, pop. G is going to come off, pop. F is going to come off, pop. And we don't have the correct order, but do you envision we could have had a set of rules using stacks that would have put these guys in order as we were bouncing back up?
Probably.
Yeah. What could we have changed? We're running low on time, but what could we have changed here? I said every single time we bounce back up, we maybe pop. Well, what could we have done? We know that F needs to be the very last thing we pop off, and we got that part, right? Got that part. But it seemed like we kind of cheated by we popped F and then put F back on. So logic says that probably that whole popping when you come back up wasn't the correct thing. Okay? So what if we took the F and we pushed it? Then when we got the B, we pushed that. But when we went to get the A, maybe we popped the B and pushed the next guy, pushing this guy back on top. Okay, but think about that from the F perspective as well. Let's go back here. When I started this, I could push the F on. Then when I visit the A, I could pop the F. I'm sorry, visit the B rather. I can pop the F, push the B with the intention of pushing this guy back on, but I haven't had that opportunity yet. So now it's a recursive call. So what happens now? The B, he's going to get temporarily popped while I push on the A. Okay, but finally the A, that's our endpoint, so we're not going to pop him again. The B is finally going to land, but not land yet. Why? Because before I can push him back on, I need to visit the right side. So I'll visit the D. So we're going to push the D on here. Okay, then we're going to visit the C. So we're going to pop the D, come and visit the C. Kind of see where this is going? All right, so we're mixing recursion with a stack to give us a breadth first search. And we'll look at that in more detail next time since we're out of time. But punchline is that visiting a tree in this way is substantially more complex than these other guys here if we try to solve it the same way. We don't have a way of conveniently traversing a tree this way because it's not built that way. All right? We can go up to the top of the Empire State Building in an elevator, and that's pretty quick. Okay? But if we were to walk around the side of the building and go, that's not made, that's not the way it was made to be traversed. That makes sense? So that's where we start needing to bring our other data structures into this. Bring a stack in. Using that stack to manipulate. When we're visiting these things, I'm going to need you in a few minutes. So I'm going to put you here, but I'm going to pop you and push you back onto the stack as I need to maintain an order. Kind of make sense? So understand that sometimes you need to use your data structures in conjunction with other data structures to get a certain thing. Okay, so having said all that, here is your programming assignment. Implement a binary tree data structure capable of holding something called a patient record. Where a patient record is a collection of details about a patient, including a first name, a last name, and an age. So instead of having a binary tree of numbers like we have now, you're going to have a binary tree of patient records. Okay? Patient record objects. Your binary tree should place patient records based on their age, where smaller ages are to the left of the root node and larger ages are to the right of the root node. Okay? Basically the same tree we had today, but we're ordering them based on a patient record's age as opposed to an integer. Well, directly an integer. In the end, your program should display the patient record in the lower left of your tree, the patient record at the root node of your tree, and the patient record in the lower right of your tree. So make sure you submit your source code through GitHub and all that stuff, and a screenshot of your program's output. Make sense what I'm asking you to do? All right, so you're going to prove that your tree is in a reasonable order by visiting the bottom left, which should be which value? Smallest of the smallest?
Yeah.
So your bottom left patient should be your youngest patient. Your bottom right patient should be your oldest patient. And what's the root node going to be? The far left is your youngest. Far right is your oldest. What's the root node going to be?
There's no order at all.
He's your first patient, right? Root node's your first patient. All right, that makes sense? All right, so should be an easier assignment, I think. That one seem like it's easier?
Yes. Much easier.
All right. Then the report, write a 2 to 3 page paper discussing the potential uses of binary trees in modern software development applications. Provide a case study of a specific software product that uses a binary tree as part of its implementation. Explain why the software product uses a binary tree over other potential data structures. All right, so as part of this, you need to go and find some software product that exists that is implemented in terms of a binary tree of some type. All right, and argue why that program uses that data structure. Make sense? Questions, comments, concerns, bribes?
See you next week.
All right.